Picture this: a single particle, smaller than an atom, hurtles through space with more energy than a major league fastball. It slams into Earth's atmosphere, creating a cascade of particles so powerful it could light up a city. This isn't science fiction, it's real. Ultra-high energy cosmic rays are crashing into our planet every day, and we still don't fully understand where they come from or how they reach such mind-bending speeds. These cosmic bullets pack energies millions of times stronger than anything we can create in our most advanced particle accelerators. They defy the laws of physics as we know them, challenging scientists to rethink what's possible in the universe. Somewhere out there, nature has built its own supercharged particle accelerators, far beyond anything humans could ever construct. Today, we're going on a journey to uncover the mystery behind these cosmic powerhouses, exploring the most extreme and violent places in the universe where particles are launched with unimaginable force. The answers might just rewrite our understanding of reality itself. So hold on tight, because we're about to dive deep into one of the greatest unsolved puzzles in astrophysics. What could possibly create these ultra-high energy cosmic rays, and what do they reveal about the hidden workings of our universe? The truth is stranger than anything we've imagined. Now let's take a step back and break down what cosmic rays actually are. Think of them as cosmic travelers, tiny but incredibly energetic particles zipping through space at nearly the speed of light. Most cosmic rays are just everyday protons or the nuclei of atoms like helium, carbon, or even heavier elements. They come in all shapes and sizes, but what really sets them apart is their energy. Some are relatively tame, what we'd call low-energy cosmic rays, still fast, but nothing too extraordinary. Then there are the ultra-high-energy cosmic rays, the rock stars of the cosmic ray world, packing energies beyond what seems physically possible. To put that into perspective, imagine a single proton with the energy of a tennis ball served at over 100 miles per hour. Now crank that up by a factor of 100 million, and you're still not close to the power of the most extreme cosmic rays. The highest energy ones exceed 10 to the power of 20 electron volts. That's a 1 followed by 20 zeros, an energy level so extreme it defies our current understanding of how particles gain speed in the universe. But here's where it gets even more fascinating. These ultra-high energy particles don't just pop into existence. They've been accelerated by something unimaginably powerful, like a cosmic slingshot firing particles across the universe. And their journey is anything but smooth. They weave through magnetic fields, dodge galaxies, and sometimes even collide with other particles, creating secondary showers that rain down on Earth. Yet despite this chaotic voyage, they arrive with almost unfathomable energy intact, forcing scientists to ask, what kind of cosmic engine could possibly launch them like this? What's really mind-bending is that even our most advanced particle colliders, like the Large Hadron Collider, can't come close to replicating these energies. Nature, it seems, has built accelerators far beyond our wildest engineering dreams. Somewhere out there, hidden in the depths of space, lies a phenomenon so violent, so energetic, that it can take a tiny particle and hurl it across the cosmos at speeds that challenge everything we know about physics. And that's what makes solving this mystery so thrilling. It's not just about cosmic rays, it's about uncovering the universe's most extreme and hidden power sources. Now here's the puzzle that keeps scientists up at night. These ultra-high-energy cosmic rays don't just push the limits, they smash right through them. Take the Large Hadron Collider, humanity's most powerful particle accelerator. It can ramp up protons to an impressive 7 trillion electron volts. But the highest energy cosmic rays, they're a million times more energetic. That's like comparing a firecracker to a supernova. So the burning question is, how does nature do what our best technology can't even come close to achieving? One major clue lies in something called the Greisen-Zatsepin-Kuzmin limit, or GZK limit for short. Think of it as a cosmic speed bump. According to physics, particles traveling at these insane energies should hit a wall. As they zip through space, they'll inevitably collide with photons from the cosmic microwave background, the afterglow of the Big Bang. These collisions should drain their energy over long distances, putting a hard cap on how energetic they can be when they finally reach us. But here's the twist. Some ultra-high-energy cosmic rays appear to ignore this rule entirely. They arrive with energies that, in theory, shouldn't be possible if they came from distant galaxies. This leaves scientists with two possibilities, both equally thrilling. Either these particles come from somewhere much closer than we thought within our cosmic backyard, or there's a wild, unknown process out there that re-energizes them mid-flight. Imagine a cosmic relay race where these particles somehow get a second wind, defying the laws we thought were set in stone. Then there's the direction problem. When astronomers trace the paths of these ultra-high-energy cosmic rays back to their origins, they often point to empty patches of space. No galaxies, no black holes, nothing that screams cosmic particle accelerator. It's like finding footprints leading to the edge of a cliff, with no sign of where the traveler came from. This suggests either our detection methods still have blind spots, or these particles are being bent and twisted by magnetic fields in ways we don't fully understand yet. What's clear is that ultra-high-energy cosmic rays aren't just outliers, they're messengers. They're telling us that somewhere in the universe there's a phenomenon we haven't discovered yet, something that operates on scales we can barely imagine. Whether it's hidden physics, undiscovered cosmic engines, or even flaws in our current theories, one thing is certain: solving this mystery won't just rewrite the rules of particle physics. It'll reveal a side of the universe we never knew existed, and that's what makes the hunt for their source one of the most exciting quests in modern science. Next up, we'll explore how scientists are actually catching these elusive particles using everything from giant detector arrays to flashes of light in the night sky. The methods are as ingenious as the mystery itself. Now let's pull back the curtain on how scientists are actually catching these cosmic speed demons. Picture a sprawling field in Argentina, dotted with 1,600 giant water tanks, each about the size of a small swimming pool. This is the Pierre Auger Observatory, one of Earth's most ambitious cosmic ray detectives. But why water tanks? Because when an ultra-high-energy cosmic ray slams into our atmosphere, it doesn't arrive quietly. It creates a spectacular subatomic fireworks show called an air shower. Here's how it works. When a single high-energy proton or nucleus from deep space collides with an air molecule, it triggers a chain reaction. The impact spawns a cascade of secondary particles, muons, electrons, pions, all racing toward the ground at near light speed. By the time this particle avalanche reaches Earth's surface, it can spread over dozens of square kilometers. Those water tanks, they're lined with ultra-sensitive light detectors that spot the faint blue glow called Cherenkov radiation, produced when these secondary particles zip through the water faster than light can travel in that medium. Think of it like capturing the sonic boom of a jet, but for particles. But the Auger Observatory has another trick up its sleeve: fluorescence detectors. These are specialized telescopes perched around the array, staring at the night sky not for stars but for ultraviolet flashes. As the air shower develops high in the atmosphere, it excites nitrogen molecules, causing them to emit a faint UV glow. This allows scientists to essentially watch the cosmic ray's footprint in real time, like tracing the path of a meteor through the sky. By combining data from both the water tanks and the fluorescence detectors, researchers can reconstruct the cosmic ray's original energy and trajectory with stunning precision. There's a beautiful irony here. To study particles smaller than an atom, we need instruments spread across an area larger than some cities, and the challenges don't stop there. Since ultra-high-energy cosmic rays are so rare, we're talking maybe one particle per square kilometer per century. the Auger Observatory has to keep watch over 3,000 square kilometers, an area bigger than Luxembourg. It's like trying to catch individual raindrops in a continent-sized net. What makes this observatory truly revolutionary is how it turns Earth's atmosphere into a giant particle detector. Instead of building an impossibly large machine to catch these cosmic rays directly, we let the air do the hard work for us. Every air shower becomes a breadcrumb trail, leading us backward to the cosmic ray's origin. And when multiple detectors pick up the same event from different angles, it's like triangulating the position of a distant explosion. Of course, even with all this ingenuity, there are still gaps in our cosmic net. Some particles arrive at such extreme energies that their air showers develop unusually high in the atmosphere, making them harder to spot. Others might come from directions where we have fewer detectors. But every new detection, every flicker of Cherenkov light or UV flash, brings us one step closer to solving the mystery of nature's ultimate particle accelerators. Next, we'll venture beyond our atmosphere to explore the cosmic powerhouses that might be launching these particles across the universe, places where physics operates on scales that dwarf even our wildest imaginations. Now let's journey to the heart of some of the most violent and energetic places in the universe: active galactic nuclei. Imagine a cosmic monster lurking at the center of a distant galaxy, a supermassive black hole millions or even billions of times heavier than our Sun. But this isn't just any black hole. It's one that's actively feeding, swallowing vast amounts of gas and dust. And as material spirals into this gravitational abyss, it doesn't go quietly. The energy released is so immense that it can outshine the entire galaxy around it, creating what astronomers call an active galactic nucleus. Here's where things get even more extreme. Some of that infalling material doesn't actually cross the black hole's event horizon. Instead, it gets funneled into powerful jets that shoot outward at nearly the speed of light. These relativistic jets, stretching for thousands or even millions of light years, are like nature's own particle accelerators, except they're on a scale that makes human-built machines like the Large Hadron Collider look like toys. The magnetic fields in these jets are unimaginably strong, twisting and contorting as they channel charged particles. And just like a surfer catching a wave, protons and atomic nuclei caught in these fields can be accelerated to dizzying energies, possibly even reaching the ultra-high levels we detect as cosmic rays. But how exactly does this work? Picture a particle caught in the jet's magnetic turbulence. Each time it crosses a shock wave or a region where the magnetic field changes direction, it gets a boost of energy, much like a pinball bouncing between bumpers. Over time, these repeated kicks can propel particles to velocities so high they rival the energies produced in the most violent cosmic events. Some researchers believe this process, called Fermi acceleration, could be the key to explaining how active galactic nuclei generate ultra-high energy cosmic rays. Yet not all active galactic nuclei are created equal. The most powerful ones, known as blazars, have jets that happen to point almost directly at Earth. From our perspective, their light appears dramatically amplified, making them some of the brightest objects in the gamma-ray sky. And intriguingly, several ultra-high-energy cosmic ray events have been tentatively traced back to the general direction of known blazars. It's still not definitive proof cosmic rays don't travel in straight lines due to intergalactic magnetic fields, but it's a tantalizing clue. Of course, there are still puzzles to solve. Not every active galactic nucleus seems capable of producing particles at the extreme energies we observe, and the exact mechanics of how particles are accelerated to such dizzying speeds remain unclear. But one thing is certain: these cosmic powerhouses remind us that when it comes to particle physics, nature often outdoes even our most ambitious experiments. Our next stop takes us to another contender in the cosmic ray mystery, gamma-ray bursts, where the universe flexes its muscles in sudden, unimaginable explosions. Now let's turn our attention to one of the most explosive events in the cosmos: gamma-ray bursts. Picture this: in just a few seconds, a single gamma-ray burst can release more energy than our Sun will emit over its entire 10 billion-year lifetime. These titanic explosions, often occurring billions of light-years away, are so bright they can briefly outshine entire galaxies, and hidden within their fury might be the secrets to how some ultra-high-energy cosmic rays are born. There are two main types of gamma-ray bursts. The short bursts, lasting less than 2 seconds, are thought to come from collisions between dense stellar corpses like neutron stars. The long bursts, which can go on for minutes, are linked to the deaths of massive stars in supernova on steroids. In both cases, the collapsing or colliding stars unleash jets of plasma moving at close to the speed of light. These jets are where the real action happens. As they plow through surrounding gas, they create shock waves that act like cosmic particle accelerators on an unrivaled scale. Here's the fascinating part. When those shock waves collide with the interstellar medium, they don't just produce the gamma rays we observe, they also generate turbulent magnetic fields. Charged particles like protons or atomic nuclei can get trapped in these fields, bouncing back and forth like pinballs in a cosmic arcade. With each bounce, they gain energy, eventually reaching velocities so extreme they could account for some of the ultra-high-energy cosmic rays we detect. This process, known as shock acceleration, is similar to what happens in active galactic nuclei, but packed into an even more violent, concentrated event. What makes gamma-ray bursts particularly compelling as cosmic ray sources is their sheer power. Some bursts emit energy equivalent to converting the entire mass of the Sun into pure radiation in mere seconds. If even a fraction of that energy goes into accelerating particles, we're talking about energies that dwarf anything possible in human-made colliders. There's also intriguing evidence from observatories like the Fermi Gamma-Ray Space Telescope, which has detected high-energy photons coinciding with some cosmic ray events, hinting at a possible connection. Yet mysteries remain. Not all gamma-ray bursts seem capable of producing particles at the highest energies, and the exact conditions required are still being modeled. Plus, because these bursts are so fleeting and their afterglows fade quickly, catching them in the act of cosmic ray production is a monumental challenge. But when we do, it could unlock answers to one of astrophysics' biggest puzzles. As we peel back the layers of these cosmic powerhouses, another contender emerges: starburst galaxies, where the chaos of star birth and death might also play a role in accelerating particles to unimaginable energies. Now let's shift our gaze to another cosmic powerhouse: starburst galaxies. These aren't your typical galaxies. They're like frenzied factories where stars are born at a rate hundreds of times faster than in our own Milky Way. Imagine a place so dense with newborn stars that their collective light outshines the rest of the galaxy. This isn't just a spectacle, it's a chaotic playground for particle acceleration. The secret lies in the turbulence. In starburst galaxies, massive stars form in tight clusters, living fast and dying young. When these stars explode as supernova, they don't just fade away quietly. They unleash shock waves that ripple through surrounding gas clouds, turning the entire region into a particle accelerator on a galactic scale. These shock waves are like cosmic bulldozers, plowing through space and giving protons and atomic nuclei the kicks they need to reach ultra-high energies. But supernova aren't the only players here. Even before these stars explode, their fierce stellar wind streams of charged particles blown outward at millions of miles per hour collide with interstellar material, creating more shock fronts where particles can gain energy. One of the best-studied starburst galaxies is Messier 82, located around 12 million light-years away. Here, supernova go off roughly every 10 years, a staggering rate compared to our galaxy's once-per-century pace. Each explosion adds to a maelstrom of accelerated particles, and astronomers have detected gamma rays from Messier 82 that suggest cosmic rays are indeed being produced in its star-forming frenzy. It's like catching a glimpse of nature's own particle collider in action. What makes starburst galaxies unique is their ability to sustain this chaos over long periods. Unlike gamma-ray bursts, which are fleeting, or active galactic nuclei, which depend on the whims of a central black hole, starburst galaxies keep churning out cosmic rays as long as they have fuel for star formation. Their dense environments also mean particles don't have to travel far to encounter another shock wave, giving them multiple chances to ramp up their energy. Yet there's a catch. While starburst galaxies are prime suspects for producing lower energy cosmic rays, whether they can reach the extreme energies we see in the highest energy particles remains debated. Some models suggest that repeated acceleration across multiple supernova remnants could do the trick, while others point to rare, hyper-energetic events within these galaxies. What's clear is that starburst galaxies are a key piece of the cosmic ray puzzle, offering a different flavor of particle acceleration compared to the one-off violence of gamma-ray bursts or the steady power of active galactic nuclei. As we piece together how these violent star factories contribute to the cosmic ray saga, another intriguing phenomenon comes into focus: tidal disruption events, where black holes turn stars into particle-accelerating debris. Now let's turn our attention to one of the most dramatic cosmic events imaginable: tidal disruption events. Picture a star minding its own business, drifting too close to a supermassive black hole. In an instant, the black hole's immense gravity stretches and compresses the star like taffy, tearing it apart in a spectacular display of destruction. This isn't just a violent cosmic spectacle, it's a potential factory for ultra-high-energy cosmic rays. When a star is ripped apart by a black hole, its material doesn't just vanish. Instead, it forms a swirling disk of superheated gas around the black hole, glowing intensely as it's devoured, but some of that material doesn't fall in. Instead, it gets funneled into powerful jets shooting out from the poles of the black hole at nearly the speed of light. These jets are like celestial particle accelerators, where magnetic fields and shock waves can whip protons and atomic nuclei up to mind-boggling energies. One of the most famous examples happened in 2018, when astronomers spotted a tidal disruption event nicknamed the Tidal Disruption Event of the Cow. The event produced an enormous flare of light and high-energy radiation, and some researchers believe it might have also unleashed cosmic rays. The sheer energy released in these events, equivalent to millions of supernovae, makes them prime candidates for producing the most energetic particles in the universe. What's fascinating is how these events differ from other cosmic ray sources. Unlike starburst galaxies, where acceleration happens gradually across multiple shocks, or active galactic nuclei, which have steady jets, tidal disruption events are sudden and unpredictable. They're like cosmic lightning, strikes brief but incredibly powerful, and because the jets are so tightly focused, they might be able to accelerate particles to even higher energies than more diffuse processes. The challenge, though, is catching these events in the act. Tidal disruption events are rare, happening maybe once every 10,000 years in a typical galaxy. But with modern telescopes scanning the skies, we're starting to see more of them, and each one offers clues about whether they are behind some of the ultra-high-energy cosmic rays we detect. While the evidence is still coming in, the math is compelling. The energies involved in these stellar shreddings are more than enough to explain the highest energy cosmic rays we've seen. And if black holes can turn stars into cosmic particle beams, it would add another piece to the puzzle of where these mysterious particles come from. As we explore these extreme events, another layer of complexity emerges: how intergalactic magnetic fields might be bending and scattering cosmic rays, making their origins even harder to trace. Now let's unravel another cosmic mystery: the invisible web of intergalactic magnetic fields. These vast, ghostly forces stretch between galaxies, shaping the paths of ultra-high-energy cosmic rays in ways that cloak their origins. Imagine throwing a handful of confetti into a windy storm. Instead of tracing straight back to your hand, the confetti swirls and scatters, making it nearly impossible to pinpoint where it started. That's exactly what happens when cosmic rays travel through these magnetic fields. These fields aren't strong, often weaker than a fridge magnet, but they're enormous, spanning millions of light years. As a cosmic ray zips through space, even a faint magnetic field can bend its trajectory, sending it on a winding detour. The higher the particle's energy, the straighter its path should be, but for the most energetic cosmic rays, the effect is still significant. By the time these particles reach Earth, their arrival directions are like smudged fingerprints, obscuring their true sources. This creates a major challenge for astronomers. It's like trying to solve a cosmic whodunit where the clues keep moving. Even if we detect a cosmic ray coming from a particular patch of sky, the actual source could be tens of millions of light years away from that spot. This is where the idea of the magnetic horizon comes into play. Just as Earth's horizon limits how far we can see, these magnetic fields create a sort of cosmic fog, beyond which we can't reliably trace particles back to their origins. The strength and structure of these fields are still poorly understood. Some might be remnants from the early universe, frozen in time like fossils. Others could be stirred up by galactic winds or collisions between galaxy clusters. What's clear is that they're not uniform. Some regions of space might have tangled magnetic spaghetti, while others are smoother, like quiet rivers. This patchwork means cosmic rays from the same source could arrive from wildly different directions, further muddying the waters. There's a tantalizing clue, though. If we could map these fields, we might reverse engineer the paths of cosmic rays. Projects like the Square Kilometre Array radio telescope aim to do just that, using faint signals from distant galaxies to trace magnetic fields. Meanwhile, simulations on supercomputers are helping physicists model how particles twist and turn through this invisible maze. The puzzle doesn't end there. Some theories suggest these fields might even trap cosmic rays for eons, creating reservoirs of high-energy particles that only occasionally escape. If true, the cosmic rays we detect could be ancient travelers, their origins hidden not just by distance but by time itself. As we peel back these layers, the next frontier emerges: how cutting-edge observatories and bold new theories are bringing us closer than ever to solving the mystery of ultra-high-energy cosmic rays. Now let's venture into the realm of the extraordinary, where the answers to ultra-high-energy cosmic rays might lie not in cosmic accelerators, but in the fabric of the universe itself. While most theories focus on how particles are boosted to extreme speeds, top-down theories flip the script entirely. Imagine a waterfall shattering into droplets as it crashes onto rocks below. Instead of asking how the droplets were tossed upward, you'd wonder what massive force broke them apart in the first place. That's the essence of top-down scenarios. Ultra-high-energy cosmic rays might be the debris of something far grander decaying or unraveling across the cosmos. One leading candidate is super-heavy dark matter, a hypothetical cousin of the mysterious substance that makes up 85% of the universe's mass. Unlike ordinary dark matter, these particles could weigh as much as a grain of sand, but packed into a single, unimaginably dense speck. If they exist, they might slowly decay over billions of years, releasing bursts of energy that fragment into the protons and nuclei we detect as cosmic rays. Picture a time bomb ticking since the dawn of time, its explosions too faint to notice except for the ultra-high-energy shrapnel they leave behind. The beauty of this idea: it wouldn't require cosmic accelerators at all. These rays would simply be the fallout of dark matter's slow-motion demise. Then there's the even wilder possibility of cosmic strings, frozen flaws in space-time left over from the universe's fiery birth. Think of them as cracks in a pane of glass, but stretching across millions of light years. If they exist, their immense tension could snap, releasing enough energy in an instant to dwarf entire galaxies. The resulting shockwaves might spawn cosmic rays with energy so high they make the "oh my god" particle look tame. While cosmic strings remain speculative, their sheer scale could explain why some cosmic rays seem to come from nowhere. Their sources might be defects in spacetime itself, invisible until they rupture. Top-down theories also open the door to other exotic ideas, like primordial black holes evaporating in a final, violent burst, or interactions involving hypothetical particles like magnetic monopoles. What unites these concepts is their defiance of conventional physics. They don't just push the boundaries of the standard model, they leap clean over them, suggesting that ultra-high-energy cosmic rays might be our first glimpse of a deeper layer of reality. Of course, these ideas are controversial. Critics point out that if super-heavy dark matter were decaying everywhere, we'd expect a steady rain of cosmic rays from all directions, not the sporadic, clustered detections we see. Cosmic strings, meanwhile, would likely leave other imprints like gravitational waves or distortions in the cosmic microwave background, which we haven't yet found. But that's the thrill of frontier science. The most daring explanations often teeter on the edge of discovery and dismissal. As we push forward, next-generation detectors and space telescopes could tilt the scales. If certain patterns in cosmic ray energies or arrival directions align with top-down predictions, we might finally crack open a window onto physics beyond our wildest theories. Until then, these ideas remain dazzling possibilities, reminders that the universe's greatest mysteries often lurk in the spaces between what we know and what we've yet to imagine. Shifting our gaze from cosmic mysteries to familiar stellar phenomena, let's revisit supernova remnants, the fiery graveyards of exploded stars. These chaotic clouds of gas and dust might not pack the punch needed to create ultra-high-energy cosmic rays, but they're cosmic classrooms for understanding how particles get their speed. Think of them as nature's particle accelerators on training wheels, showing us the basics before we tackle the universe's extreme extremes. When a massive star dies in a supernova, it doesn't go quietly. The explosion blasts material outward at speeds approaching 1/10 the speed of light, creating shock waves that ripple through space for thousands of years. These shocks act like natural racetracks for charged particles, with magnetic fields serving as bumpers that keep protons and atomic nuclei circling faster and faster. Each pass pumps more energy into them, much like a surfer catching wave after wave to build momentum. The result, particles with energies up to 1,000 trillion electron volts, energetic enough to qualify as cosmic rays, though still far short of the ultra-high-energy champions we've been hunting. What makes supernova remnants so valuable is their proximity. Unlike distant active galaxies or hypothetical cosmic strings, these stellar wreckages are scattered throughout our Milky Way, some just hundreds or thousands of light-years away. This closeness lets scientists study them in stunning detail, using telescopes like Chandra and Fermi to map their tangled magnetic fields and measure particle energies directly. The Crab Nebula, for example, is a textbook case. Its swirling filaments glow with synchrotron radiation, a telltale sign of electrons spiraling near light speed, while its pulsar heart pumps out particles like a cosmic fire hose. The real lesson here isn't just about raw power, but process. Supernova remnants demonstrate Fermi acceleration in action, the same mechanism thought to operate in far more violent environments. When particles bounce between colliding shock fronts like pinballs ricocheting between moving bumpers, they can gain enormous energy over time. Scaling this up to the extreme conditions around supermassive black holes or gamma-ray bursts might explain how nature achieves those jaw-dropping ultra-high energies. Yet supernova remnants have limits. Even the most powerful shocks can't boost particles beyond a certain threshold, like a car engine redlining before it hits light speed. That's why researchers see them as stepping stones to more exotic sources. By decoding how they accelerate particles, we can refine models for extreme environments where the rules might stretch or break entirely. So while supernova remnants might not solve the ultra-high-energy puzzle outright, they're far from cosmic footnotes. They're living labs showing us how the universe tinkers with particle acceleration on scales we can actually observe. And sometimes understanding the ordinary is the key to unraveling the extraordinary. Now, let's dig into the engine behind particle acceleration, nature's own cosmic speed boost known as Fermi acceleration. Picture a game of interstellar pinball where charged particles ricochet between shock waves in space, gaining a little more energy with every bounce. This isn't just a theory confined to textbooks, it's the universal process that powers cosmic rays across the universe, from our Milky Way's backyard to the most distant galaxies. The magic happens in two flavors. First-order Fermi acceleration, often called shock drift, works like a particle surfing on a shock wave. Imagine a magnetic field moving through space. Particles caught in its path get a forward kick each time they cross the shock, like a surfer timing the perfect wave. But the real powerhouse is second-order Fermi acceleration. Here, particles bounce between turbulent magnetic fields or colliding shock fronts, gaining energy from chaotic head-on collisions. Think of it as a cosmic version of a ping-pong ball trapped between two closing paddles. Each hit sends it flying faster. What makes this process universal is its scalability. In supernova remnants, Fermi acceleration can boost protons to petaelectronvolt energies, that's 1,000,000 billion electron volts, but crank up the environment to something more extreme, like the relativistic jets of an active galactic nucleus, and the same basic physics could propel particles to those elusive ultra-high energies. The key difference, the speed of the shocks and the strength of the magnetic fields. Near a supermassive black hole, shocks might travel at 99% the speed of light, with magnetic fields billions of times stronger than Earth. That's like upgrading from a backyard trampoline to a particle cannon. Scientists see echoes of this scaling in cosmic ray observations. The energy spectra of particles, how their numbers drop off at higher energies, follow a near-perfect power law across many orders of magnitude. That mathematical consistency hints that the same fundamental process, Fermi acceleration, operates everywhere, just dialed up or down based on the environment's violence. Even solar flares use a miniaturized version of this mechanism to spit out high-energy protons. Yet puzzles remain. Fermi acceleration struggles to explain the very highest energy cosmic rays without some extra help, maybe additional turbulence in magnetic fields or multiple shock layers working in concert. That's where cutting-edge simulations come in. Supercomputers now model how particles navigate these extreme environments, revealing that under the right conditions, Fermi processes might just breach the ultra-high-energy frontier. So whether it's a dying star's last gasp or a black hole's jet, the universe relies on this elegant mechanism to turn ordinary particles into cosmic speedsters. Understanding Fermi acceleration isn't just about solving the mystery of ultra-high-energy cosmic rays. It's about decoding the universe's favorite way to make things move fast. And sometimes the most profound cosmic secrets hide in plain sight, written in the physics of a bouncing particle. Now, let's pivot to the cosmic particle collisions that fuel these high-energy events. While Fermi acceleration gets particles moving, it's the actual interactions, protons smashing into other protons or photons, that generate the cosmic rays we detect. These two mechanisms dominate different corners of the universe, each leaving its own fingerprint on the particles we observe. First, proton-proton collisions. Picture the crowded core of a starburst galaxy, where dense gas clouds and stellar winds pack protons together like commuters in a rush-hour subway. When two protons collide here, they shatter into a spray of secondary particles, pions, kaons, and other fragments. The charged pions then decay into the cosmic rays we detect, primarily protons and helium nuclei. This process thrives in chaotic, high-density environments, from supernova remnants to galaxy clusters. The telltale sign, a steady stream of gamma rays from decaying neutral pions, which telescopes like Fermi LT spot across our galaxy. But head to the radiation-drenched zones near active galactic nuclei or gamma-ray bursts, and proton-photon interactions take over. Here, protons don't collide with other protons, they crash into the sea of high-energy photons flooding these regions. A proton meeting a gamma-ray photon can spawn a delta particle, which quickly decays back into a proton and charged pions. Or, if the photon's energy is just right, the proton might absorb it entirely, becoming unstable and shedding its excess energy by creating new particles. This photonuclear process dominates where radiation outweighs matter, like in the relativistic jets of quasars. The key difference lies in their energy outputs. Proton-proton collisions are democratic. They produce a broad range of particle energies like a shotgun blast. Proton-photon interactions, by contrast, are snipers. They're pickier about the photon energies they require but can catapult particles to extreme velocities when conditions align. That's why we suspect proton-photon reactions in AGN jets might be the key to ultra-high-energy cosmic rays. And here's the cosmic twist: these processes leave different chemical signatures. Proton-proton collisions favor heavier elements like carbon or iron, since they occur in star-forming regions littered with stellar debris. Proton-photon interactions happening in purer radiation fields tend to spit out lighter particles. So by studying the mix of elements in cosmic rays, scientists can essentially read the universe's recipe. Was this particle forged in a crowded stellar nursery or a photon-blasted jet near a black hole? Yet both mechanisms share one profound limit: the GZK cutoff. Even the most energetic protons from these interactions should lose energy over intergalactic distances by bumping into the cosmic microwave background. The fact that we detect particles beyond this limit suggests there's still more to uncover about nature's particle forges. Whether it's proton-proton chaos in galactic cores or proton-photon duels near black holes, these collisions remind us that the universe doesn't just accelerate particles, it orchestrates their creation with particle physics precision. Now, let's unravel one of the most intriguing clues in this cosmic detective story: the way these ultra-high-energy cosmic rays don't rain down evenly across the sky. Instead, they arrive in patches like scattered footprints hinting at hidden sources. This uneven distribution, known as anisotropy, is our best lead for tracing these particles back to their origins. Picture the night sky as a vast ocean and cosmic rays as raindrops falling unevenly across its surface. Some areas get drenched while others stay almost dry. Scientists expected these particles to arrive uniformly from all directions, given how magnetic fields in space should scramble their paths over millions of light years. But reality loves surprises. Observations reveal clusters of ultra-high-energy events, some grouped tightly enough to suggest they're coming from the same distant powerhouse. Take the hotspot spotted by the telescope array in Utah. Over nearly 2 decades, this observatory recorded a concentration of cosmic rays with energies above 57 billion electron volts. These events clustered near the constellation Ursa Major, pointing towards something colossal in that patch of sky. Could it be a nearby active galaxy? A dense knot of intergalactic magnetic fields funneling particles our way. The puzzle deepens because no obvious single source stands out in that direction. Then there's the broader asymmetry, a lopsidedness in the sky. Data from the Pierre Auger Observatory shows slightly more ultra-high-energy cosmic rays arriving from one half of the sky than the other. This imbalance might trace back to our local supercluster of galaxies, where matter isn't spread evenly. Imagine cosmic rays getting a slight nudge from the gravitational pull or magnetic fields of nearby galaxy clusters, creating this faint but detectable tilt. The real challenge: magnetic fields act like cosmic hallways, bending the paths of these charged particles in unpredictable ways. A cosmic ray arriving from the left might have started its journey far to the right, twisted by magnetic detours. This makes pinning down exact sources like trying to trace a ricocheted bullet back to the shooter. Yet, the fact that some anisotropy exists at all is a revelation. It tells us these particles aren't coming from everywhere equally. There's structure, and that structure whispers hints about the engines behind them. Recent advances are sharpening the picture. Combining data from multiple observatories, scientists are mapping these cosmic ray hotspots with better precision. Some align tantalizingly close to known active galactic nuclei or starburst galaxies, while others remain mysteries, possibly hinting at entirely new classes of cosmic accelerators. Every new ultra-high-energy event adds another dot to this connect-the-dots puzzle, and with enough dots, the universe's hidden blueprints might finally come into view. What's clear is this anisotropy isn't just noise. It's a signal, a coded message about where and how nature's most powerful particle accelerators operate. And as our detectors grow more sensitive, we're one step closer to cracking that code. Now, let's turn our attention to another piece of this cosmic puzzle, the elusive neutrino. These ghostly particles might just hold the key to unraveling the origins of ultra-high-energy cosmic rays. Unlike charged particles, neutrinos travel through space in near-perfect straight lines, unaffected by magnetic fields. That means when we detect one, we can trace its path back to its source with remarkable precision. Think of them as cosmic messengers, delivering untampered clues about the universe's most violent events. The IceCube Neutrino Observatory, buried deep in the Antarctic ice, is our frontline detector for these high-energy neutrinos. When a neutrino interacts with the ice, it creates a faint flash of light, a signal IceCube's sensors capture. What makes this so exciting? Some of these neutrinos pack energies rivaling those of ultra-high-energy cosmic rays, suggesting they're born in the same extreme environments. If we can link a high-energy neutrino to a specific event like a flaring active galaxy or a gamma-ray burst, we might finally pin down the accelerators behind cosmic rays. This is where multi-messenger astronomy shines. Instead of relying on just one type of signal, scientists combine data from cosmic rays, neutrinos, and gamma rays to build a fuller picture. Imagine putting together a jigsaw puzzle where each piece comes from a different angle. In 2017, IceCube detected a neutrino with energy around 290 trillion electron volts. Alerted by this, telescopes worldwide swung into action, pinpointing its origin to a blazar, a supermassive black hole shooting jets straight at Earth. This marked the first time a high-energy neutrino was tied to a specific astrophysical source, a breakthrough that hinted at blazars as potential cosmic ray factories. But neutrinos are notoriously hard to catch. They pass through entire planets like they're not even there, which means detectors like IceCube have to be massive to stand a chance. Even then, we're only catching a tiny fraction, yet every detection is precious. When a high-energy neutrino arrives alongside a cosmic ray or gamma ray from the same direction, it's like finding matching fingerprints at a crime scene. The real power of this approach lies in its ability to cross-check theories. If a cosmic ray hotspot overlaps with a neutrino flare and a gamma ray burst, the case for that source being a cosmic ray accelerator grows stronger. Recent studies suggest that starburst galaxies and tidal disruption events might also emit neutrinos, adding more candidates to our list. With upgrades to IceCube and new detectors on the horizon, we're entering an era where these invisible messengers could illuminate the darkest corners of the cosmos. So, while neutrinos might be the universe's most elusive particles, they are also some of its most revealing. By combining their clues with other cosmic signals, we're not just solving a mystery, we're rewriting the story of how the universe's most powerful particles are born. Now, let's zoom in on another fascinating layer of this cosmic detective story: hidden patterns in the arrival directions of ultra-high-energy cosmic rays. When scientists map where these particles come from, they don't see a random scatter. Instead, they find intriguing clusters like stars forming constellations in the night sky. But what do these clusters really tell us? One of the biggest challenges is the sheer rarity of these events. Imagine trying to solve a puzzle with only a handful of pieces. Ultra-high-energy cosmic rays are so few and far between that even after decades of observation, we've only detected a few dozen with energies above 100 trillion electron volts. This makes spotting reliable patterns incredibly difficult. Yet, when researchers sift through the data, certain areas of the sky seem to attract more of these particles than others. Take the so-called hotspot near the constellation Ursa Major, first noted by the Telescope Array project. This region, roughly 20 degrees across, shows a higher concentration of ultra-high-energy cosmic rays than expected by chance. Could this be a signpost pointing to a nearby cosmic accelerator, perhaps a turbulent galaxy or a hidden black hole? The answer isn't straightforward. Magnetic fields crisscrossing the universe bend the paths of these charged particles, smearing their arrival directions like fingerprints on glass. By the time they reach Earth, their trajectories may lead us in the wrong direction, masking their true origins. Then there's the question of whether these clusters come from single, powerful sources or broader, diffuse processes. Some theories suggest that a handful of extreme objects like active galactic nuclei or gamma-ray bursts could be responsible for multiple events in a cluster. Others argue that the particles might be accelerated across vast regions of space, like shocks from colliding galaxy clusters. Without more data, it's like trying to tell if a handful of raindrops came from one cloud or a whole storm front. The stakes are high. If clustering points to discrete sources, it could revolutionize our understanding of particle acceleration in the universe. But if it's just noise or the result of tangled magnetic fields, we might need to rethink our detection strategies. To untangle this, scientists are combining data from multiple observatories, stacking cosmic ray detections like layers in a composite image. With upgrades like the Auger project enhancing sensitivity, we might soon have enough pieces to see the full picture. What makes this search so compelling is its potential to reveal the invisible architecture of the cosmos. Every cluster, every hotspot, is a whisper from the universe's most violent corners. And as our detectors grow more precise, these whispers could turn into shouts, guiding us straight to nature's ultimate particle accelerators. Now let's turn our gaze to the horizon, where the next generation of cosmic ray detectors promises to crack this case wide open. The key to solving the mystery of ultra-high-energy cosmic rays isn't just more data, it's better data. And that's exactly what cutting-edge upgrades like the Auger project are designed to deliver. Currently, the world's largest cosmic ray observatory, the Pierre Auger Array in Argentina, is getting a major overhaul. The Auger upgrade equips its existing detectors with new scintillator panels, enhancing their ability to distinguish between protons and heavier nuclei in cosmic rays. Why does this matter? Because knowing the composition of these particles, whether they're lightweight protons or heavier atomic nuclei, helps scientists trace their paths back through intergalactic magnetic fields. It's like upgrading from a blurry telescope to one with high-definition clarity. With this sharper vision, researchers hope to pinpoint whether cosmic ray hotspots truly align with known cosmic accelerators like active galaxies, or if we're missing something even more exotic. But the innovations don't stop there. Imagine a detector so vast it could cover an area the size of a small country. That's the ambition behind the Giant Radio Array for Neutrino Detection, or GRAND. This proposed network of 200,000 radio antennas, spread across mountain ranges and deserts, would listen for the faint radio whispers of cosmic rays and neutrinos interacting with Earth's atmosphere. Unlike traditional detectors that rely on fleeting air showers, GRAND radio antennas could catch signals from ultra-high-energy particles day or night, in clear weather or storms. Its sky coverage would be unparalleled, scanning nearly the entire celestial sphere for cosmic ray sources. If built, GRAND could be the game-changer that finally maps the universe's particle accelerators with precision. Meanwhile, projects like the Telescope Array's expansion in Utah and the planned Northern Wide Field Gamma Ray Observatory are doubling down on hybrid detection techniques. By combining surface detectors with fluorescence telescopes cameras that capture the ultraviolet glow of air showers, these observatories aim to cross-check their findings, reducing uncertainties in energy and direction measurements. Think of it as solving a puzzle by comparing two separate snapshots of the same event. The future isn't just about bigger detectors, though. Supercomputers are playing a crucial role, simulating how cosmic rays traverse magnetic fields and interact with the cosmic microwave background. These virtual experiments help researchers test which theoretical sources like titanic black hole jets or decaying dark matter could produce the patterns we see. Together with next-gen hardware, they form a powerful toolkit for unraveling the universe's most energetic secrets. What's thrilling is that these advancements aren't distant dreams. Auger Prime is already collecting data, and grand prototype arrays are proving the concept works. Within the next decade, we could witness breakthroughs that rewrite our understanding of cosmic rays, and perhaps reveal entirely new physics hiding in the depths of space. The detectors of tomorrow are being built today, and with them, we're inching closer to answering one of astrophysics' greatest riddles. Where do these unimaginably powerful particles come from? While our eyes are fixed on the skies, some of the most groundbreaking detective work happens inside supercomputers, where scientists recreate cosmic ray journeys through virtual space. These digital laboratories offer a backstage pass to processes we can't directly observe, simulating how ultra-high-energy particles navigate the universe's chaotic highways. Picture this: a proton blasted from a supermassive black hole's jet travels millions of light years, zigzagging through tangled magnetic fields between galaxies. Tracing its path isn't just about plotting points on a map, it's about accounting for every twist and turn in an invisible obstacle course. That's where magnetohydrodynamic simulations come in. By modeling how plasmas and magnetic fields interact, these simulations reveal how cosmic rays might scatter or gain energy during their epic trips. Supercomputers like those at national labs crunch mind-boggling numbers to mimic these conditions. They divide intergalactic space into virtual grids, each cell calculating factors like magnetic field strength, particle collisions, and energy loss from interactions with the cosmic microwave background. Some simulations even incorporate hypothetical sources, say, a flaring active galaxy or a collapsing star, to see if their predicted cosmic rays match what detectors observe. What makes this so revolutionary? Previously, scientists relied on rough estimates of magnetic field strengths between galaxies. Now, with advanced simulations, they can test how different field configurations would bend or delay particles. For instance, if a cosmic ray seems to point toward empty space, simulations might show it was deflected by a magnetic field we hadn't mapped. This helps narrow down the true origins, separating cosmic illusions from actual sources. One fascinating breakthrough came when simulations revealed that certain particle energies should be lost due to interactions with photons from the early universe, a prediction known as the GZK cutoff. The fact that we still detect particles beyond this limit either means our models are missing something, or that sources are closer than we thought. Collaborations like the CR-Proper software framework let researchers tweak variables, source types, magnetic fields, particle compositions, and compare the virtual results with real-world data. It's like having a cosmic ray video game where every level tests a new astrophysical scenario. These digital experiments don't replace detectors, they guide them. When simulations suggest certain galaxies or events could produce specific particle signatures, telescopes can prioritize observing those targets. Together, silicon and steel are unraveling a mystery written in the universe's most energetic handwriting. As we stand at this crossroads of computation and observation, one truth becomes clear. Unlocking the secrets of cosmic rays demands both the brute force of supercomputers and the precision of next-gen detectors. The answers may lie in lines of code as much as in starlight. Now let's turn our gaze to one of the most tantalizing possibilities in cosmic ray research. What if these ultra-high-energy particles are whispering secrets about dark matter? It's a question that bridges two of astrophysics' greatest mysteries. While dark matter remains invisible, its gravitational fingerprints are everywhere, from galaxy rotations to the cosmic web. Could it also leave traces in the form of cosmic rays? One compelling idea is that dark matter particles, when they collide or decay, might unleash bursts of high-energy protons or atomic nuclei, essentially becoming invisible cosmic accelerators. Imagine a hypothetical dark matter particle, far more massive than anything in the standard model, finally meeting its end after billions of years. Its demise could release enough energy to rival the most violent astrophysical events, spraying ultra-high-energy particles across the universe. Scientists have mapped out scenarios where dense regions of dark matter, like the halos around galaxies, act as hidden factories for cosmic rays. If dark matter particles annihilate upon contact, the resulting energy might produce secondary particles, including the protons and nuclei we detect as cosmic rays. Alternatively, if dark matter is unstable over cosmic timescales, its slow decay could emit high-energy radiation, contributing to the cosmic ray flux. The search for this connection isn't just theoretical. Experiments like the Alpha Magnetic Spectrometer on the International Space Station and ground-based gamma-ray telescopes scan the skies for anomalies, excess particles, or unexpected energy patterns that could betray dark matter's presence. For instance, an unexplained surplus of positrons in certain cosmic ray data initially sparked excitement, though pulsars and other astrophysical sources now seem more likely culprits. Yet the puzzle persists. Some ultra-high-energy cosmic rays arrive from directions with no obvious astrophysical sources, leading researchers to wonder if dark matter clumps or exotic particles could be responsible. Simulations suggest that if dark matter decays uniformly across the universe, it might produce a diffuse background of cosmic rays, subtly altering their distribution compared to point sources like active galaxies. The stakes are high. Confirming a link between cosmic rays and dark matter wouldn't just solve one mystery, it could crack open the door to an entirely new realm of physics. Until then, scientists keep sifting through the data, chasing shadows in the hope that nature's most elusive substance might reveal itself through the universe's most energetic particles. What we learn could redefine not just cosmic rays but our entire understanding of matter itself. Now let's zoom in on one of the most jaw-dropping moments in cosmic ray science, the detection of the so-called "oh my God" particle. Back in 1991, scientists working at the University of Utah's Fly's Eye detector spotted something unbelievable. A single cosmic ray hit Earth's atmosphere with an energy of around 300 exa-electron volts. That's more than 40 million times the energy of protons colliding in the Large Hadron Collider. The researchers were so stunned that one reportedly exclaimed, "Oh my God." And the name stuck. This particle wasn't just a fluke. Over the years, other ultra-high-energy cosmic rays have been detected, each packing energies that defy expectations. These events are so rare that observatories might catch only a handful over decades. Yet every time one arrives, it forces scientists to rethink what's possible in the universe. The sheer power of these particles suggests they're coming from environments far more extreme than even the most violent black holes or gamma-ray bursts. So what could possibly crank particles up to such ludicrous speeds? One leading idea points to active galactic nuclei, where supermassive black holes launch jets of plasma at nearly the speed of light. If a particle gets caught in these relativistic jets, it could surf magnetic shockwaves like a cosmic pinball, gaining enormous energy along the way. Another theory involves tidal disruption events when a star gets torn apart by a black hole. The resulting explosion might act like a natural particle cannon, firing off ultra-high-energy debris. Then there's the dark matter angle we just explored. If certain heavy dark matter particles decay or annihilate, they could release bursts of energy capable of producing these extreme cosmic rays. It's a long shot, but the odd distribution of some ultra-high-energy events coming from seemingly empty patches of space keeps this idea alive, the wild card. New physics. Some researchers speculate that unknown processes like defects in spacetime itself or exotic quantum fields might be at work. If conventional astrophysics can't fully explain these particles, we might need to rewrite the rules. Whatever their source, these cosmic rays are nature's way of showing off. They push the limits of our understanding, daring us to imagine what else might be lurking in the cosmos. And with next-generation detectors coming online, we might finally get the clues needed to solve this high-energy mystery. One thing's certain, when the next "oh my god" particle arrives, it'll remind us just how much we still have to learn. Now let's venture into the realm of radical possibilities. What if the answers to these ultra-high-energy cosmic rays lie beyond the boundaries of known physics? When conventional astrophysics struggles to explain phenomena, scientists sometimes turn to unconventional ideas, and the mystery of these cosmic rays is no exception. One such theory involves the violation of Lorentz invariance, a cornerstone of Einstein's theory of relativity. This principle dictates that the laws of physics remain the same for all observers, no matter their speed or direction. But if Lorentz invariance were to break down at extreme energies, it could mean particles travel faster than expected, or energy thresholds like the Greisen-Zatsepin Kuzmin limit no longer apply. Some models suggest that tiny, spacetime altering effects at quantum scales could allow particles to reach energies that should, in theory, be impossible. Then there's the mind-bending concept of extra dimensions. String theory proposes that our universe might have more than the 3 spatial dimensions we experience, with these hidden dimensions curled up at incredibly small scales. If true, particles interacting with these extra dimensions could gain energy in ways we don't yet understand, potentially explaining the absurd power of ultra-high-energy cosmic rays. Imagine particles leaking into higher dimensions, accelerating beyond our universe's usual limits, then returning with energies that defy explanation. Another fringe but fascinating idea involves cosmic defects like topological knots or cracks in spacetime left over from the early universe. These defects, if they exist, could release bursts of energy as they decay or interact, creating ultra-high-energy particles in the process. Think of it like cracks in ice releasing pressure. Spacetime itself might harbor similar imperfections that occasionally unleash cosmic fireworks. But perhaps the most speculative theory ties ultra-high-energy cosmic rays to the birth of the universe itself. Some researchers suggest these particles could be relics from the Big Bang, frozen in time until they finally reach us, carrying energies from the universe's most violent epoch. It's a long shot, but if true, these cosmic rays would be like messages from the dawn of time, offering clues about conditions we can only theorize about today. Of course, these ideas are far from proven, and many physicists remain skeptical. Yet the sheer extremity of ultra-high-energy cosmic rays forces us to consider every possibility, no matter how unconventional. After all, history has shown that some of science's greatest breakthroughs came from questioning the unshakable. Whether it's tweaking relativity, unlocking hidden dimensions, or uncovering flaws in spacetime itself, the search for answers might just rewrite physics as we know it. And with that, we're left with a tantalizing question. Could the next "oh my god" particle be the key to uncovering an entirely new layer of reality? Now let's bring this cosmic mystery down to Earth, literally. While ultra-high-energy cosmic rays might seem like distant, abstract phenomena, they actually interact with our planet in ways that could have real-world consequences. Every second, countless cosmic rays bombard Earth's atmosphere, though most are low-energy particles that pose no threat. But what about those ultra-high-energy outliers? Could something so rare and fleeting actually leave a mark on our world? The answer might surprise you. First, consider their effect on our atmosphere. When an ultra-high-energy cosmic ray collides with an air molecule, it triggers a cascade of secondary particles, a process that can temporarily alter atmospheric chemistry. Some researchers speculate that these interactions might influence cloud formation by ionizing molecules in the upper atmosphere, though the evidence remains inconclusive. Still, it's a reminder that even particles from deep space can play a subtle role in Earth's delicate systems. Then there's the more dramatic question: could these cosmic rays have shaped life itself? One controversial theory suggests that periods of increased cosmic ray exposure might correlate with mass extinctions. The idea is that a nearby supernova or gamma-ray burst could flood Earth with high-energy radiation, damaging the ozone layer and exposing life to harmful ultraviolet light. While ultra-high-energy cosmic rays are far rarer, their extreme energy could theoretically cause similar damage on a smaller scale. Imagine a single particle with the energy of a baseball pitch striking a cell's DNA. Could that trigger mutations or even drive evolutionary change? It's a tantalizing thought, though far from proven. On a smaller scale, cosmic rays are already part of our daily lives. Ever boarded a plane and wondered about radiation exposure? Cosmic rays contribute to the background radiation we encounter at high altitudes. Pilots and frequent flyers receive slightly higher doses, though still well below dangerous levels. Ultra-high-energy cosmic rays, however, are so rare that their direct impact on individuals is negligible. You'd need an unimaginable stroke of bad luck or extraordinary fortune, depending on your perspective, to be hit by one. Yet the bigger picture is what fascinates scientists. If ultra-high-energy cosmic rays can influence atmospheric chemistry or even life's evolution, they become more than just a cosmic curiosity. They're a thread woven into Earth's story. And while we don't need to fear them, they remind us that our planet is part of a much larger, dynamic universe. From the air we breathe to the DNA in our cells, the cosmos might leave traces we're only beginning to detect. With that in mind, let's turn to another intriguing angle: how public perceptions of cosmic rays sometimes veer into the realm of myth and misunderstanding. Now let's clear up some of the most persistent myths about cosmic rays that have taken root in popular culture. Despite their dramatic origins in deep space, these particles have been misunderstood and exaggerated in ways that often stray far from reality. One of the most common misconceptions is that cosmic rays are deadly, death rays zapping everything in their path. In truth, while they do carry immense energy, the vast majority are harmless by the time they reach Earth's surface. Our atmosphere acts as a natural shield, absorbing and breaking down these particles long before they can reach us. Even the rare ultra-high-energy cosmic rays lose most of their punch through atmospheric interactions. You'd have better odds of winning the lottery than being harmed by one directly. Then there's the bizarre notion that cosmic rays cause spontaneous human combustion. This myth likely stems from their mysterious origin and the human tendency to link the unknown with sensational explanations. In reality, there's zero scientific evidence connecting cosmic rays to such phenomena. Most cases of so-called spontaneous combustion have far more mundane explanations, like electrical faults or overlooked ignition sources. Another widespread belief is that cosmic rays are a major health threat, especially for air travelers. While it's true that exposure increases at higher altitudes, the actual risk is minimal. A typical transatlantic flight exposes you to roughly the same radiation as a chest X-ray, enough to be measurable but nowhere near dangerous levels. Even astronauts on the International Space Station who face significantly higher exposure are carefully monitored and protected. Some also fear that cosmic rays could trigger technological catastrophes like frying electronics or causing planes to fall from the sky. While it's true that high-energy particles can occasionally disrupt sensitive microchips, a phenomenon called single-event upset, modern systems are designed with safeguards against such rare events. Your smartphone is far more likely to malfunction from a software glitch than a cosmic ray strike. The reality is that cosmic rays are a constant, quiet background presence in our lives. They've been streaming through Earth and through you for billions of years without causing mass destruction or mutation. If anything, they serve as a humbling reminder of our connection to the cosmos, not as a source of danger. With these myths put to rest, we can appreciate cosmic rays for what they truly are: fascinating natural phenomena that push the boundaries of physics without posing any real threat to our daily lives. This brings us to another layer of the cosmic ray story: how scientists grapple with the ethical balance between studying these particles and allocating resources to other pressing research. Now, shifting our focus to the broader impact of studying these cosmic mysteries, let's examine the ethics of cosmic ray research. This isn't just about unraveling the secrets of the universe, it's also about how we allocate limited scientific resources in pursuit of knowledge that may not have immediate, obvious benefits. One of the central ethical questions is whether funding ultra-high-energy cosmic ray studies is justified when other pressing scientific challenges, like climate change or medical research, compete for the same resources. After all, cosmic rays don't directly threaten human health or infrastructure, unlike pandemics or environmental crises. But here's the counterpoint: fundamental research, including studies of cosmic rays, often lays the groundwork for breakthroughs we can't yet foresee. For example, the development of the World Wide Web emerged from particle physics research at CERN, proving that curiosity-driven science can revolutionize everyday life in unexpected ways. Another ethical consideration is the global distribution of research efforts. Cosmic ray observatories like the Pierre Auger array are often located in remote, sparsely populated regions, raising questions about land use and local community impact. While these facilities bring scientific prestige and sometimes economic benefits to host countries, they must also address concerns like environmental disruption or indigenous land rights. Striking this balance requires transparency and collaboration with local stakeholders, ensuring that the pursuit of cosmic knowledge doesn't come at the expense of people on the ground. Then there's the question of scientific priorities. Some argue that studying cosmic rays is a luxury compared to more practical research until you consider the spin-offs. Technologies developed for cosmic ray detection, such as advanced scintillator materials or ultra-sensitive photodetectors, have found applications in medical imaging and radiation therapy. Even the algorithms used to analyze cosmic ray data are now helping artificial intelligence systems recognize patterns in everything from weather forecasts to financial markets. These unintended benefits highlight how niche research can ripple outward, touching fields far beyond astrophysics. Critics might also ask whether the high costs of building and maintaining cosmic ray observatories are justified. Projects like the proposed giant radio array for neutrino detection require significant investment, often funded by taxpayer money. Yet history shows that cutting-edge facilities frequently pioneer technologies later adopted by industry. The superconducting magnets used in MRI machines, for instance, trace their origins to particle accelerators. By pushing the limits of detection, cosmic ray research inadvertently drives engineering innovation that eventually trickles down to society. Ultimately, the ethics of cosmic ray research hinge on a broader philosophical debate. How much should humanity invest in understanding the universe for its own sake? While practical applications matter, there's also intrinsic value in exploring the unknown. cosmic rays remind us of our place in a vast, dynamic cosmos, a perspective that can inspire new generations of scientists and thinkers. And as we've seen time and again, the tools built to satisfy scientific curiosity often end up transforming the world in ways no one could have predicted. With these ethical dimensions in mind, we're ready to wrap up our journey through the enigmatic world of ultra-high-energy cosmic rays, but not before reflecting on what their mysteries might still reveal. As we bring our exploration to a close, let's take a moment to piece together the cosmic puzzle we've been unraveling. Ultra-high-energy cosmic rays remain one of the most tantalizing mysteries in astrophysics, with their origins hidden somewhere in the vast expanse of the universe. From the colossal power of active galactic nuclei to the explosive fury of gamma-ray bursts, and even the turbulent chaos of starburst galaxies, nature's particle accelerators continue to defy our expectations. Yet despite decades of research, these cosmic enigmas refuse to give up their secrets easily. What makes this quest so thrilling is the sheer scale of the challenge. These particles pack energies millions of times greater than anything we can produce in our most advanced labs on Earth. They travel across billions of light years, bent and twisted by intergalactic magnetic fields, leaving us with only faint clues to trace them back to their sources. And while observatories like the Pierre Auger Array and IceCube have brought us closer to answers, the full picture remains just out of reach. But here's the exciting part: every new discovery has the potential to rewrite the textbooks. Imagine if we finally pinpointed the true source of these cosmic rays. It wouldn't just solve a century-old mystery, it could unlock entirely new chapters in physics. We might uncover exotic particles beyond the standard model, or even stumble upon evidence of cosmic phenomena we've never dreamed of. The implications stretch far beyond astrophysics, potentially reshaping our understanding of dark matter, quantum gravity, and the very fabric of space-time. Of course, the journey doesn't end here. Next-generation detectors like Auger Prime and the giant radio array for neutrino detection are poised to push the boundaries even further. With sharper resolution and wider sky coverage, these instruments could finally crack the code of cosmic ray origins. And as supercomputers grow more powerful, simulations will help us test theories with unprecedented precision, bridging the gap between speculation and discovery. So what's your take on this cosmic whodunit? Do you think supermassive black holes are the prime suspects, or are you betting on something more exotic like decaying dark matter? Drop your favorite theory in the comments below. I'd love to hear your thoughts. And if you've enjoyed this deep dive into the universe's most energetic particles, don't forget to hit that like button and subscribe for more mind-bending explorations. Who knows, the next big cosmic revelation might be just around the corner, and you won't want to miss it. Until then, keep looking up. The universe has plenty more secrets to share.